Thanks for the introduction, Isaac. Yeah, I'm Neev Parikh. A couple months ago, we came out with R&D Bench, which is what we think is some of the best evaluations for AI R&D capabilities. And I'm here to talk about that and also other stuff that we're trying to do. Yeah, I think the best setup for questions, maybe if you have something that's like confusing or you don't really understand it, just interrupt me. And then if you have like discussion-y questions, then maybe we can try and do some of that at the end. Cool. Yes, I think most of you guys are pretty familiar with a bunch of the basic stuff, so I'm just gonna skip that. And then we're gonna go like maybe straight to like the more technical details. But yeah, cool. So overview, RE Bench has 7 tasks. The idea of RE Bench was basically a bunch of the evals that we saw that were like trying to measure like, ML performance or, software engineering performance. They had some problems when it came to trying to measure like AI R&D capabilities. Some of them weren't grounded, like we didn't have actual humans to baselines to compare to. They weren't all that realistic. Not the Kaggle challenges are not quite the same as like frontier ML work. And so we tried to address some of these problems by making some really hard tasks and paying really, really good people to try to do the best they could on these tasks. Yeah, and so this is roughly what I'm going to be going over. Some of this is edited, so maybe not the threat model because you guys kind of probably already know this. But we're going to talk about what the tasks actually look like, and we're going to talk about the results, which is, I think, where I'm going to spend the most of my time, and then some in-progress work, and then questions. Sound good? Cool. Right, so environments for RE Bench. So I think the thing that we really wanted when we were trying to design these tasks were we wanted a low floor and a really high ceiling. You want to be able to measure like small amounts of performance by models, like if they're not quite good. You don't want it to be so hard as a task that you can't really make any progress within like 6 hours or something. Like that would be somewhat hard because you do not have any signal at the low end. But you also don't want to saturate because most benchmarks are saturating at a terrifying rate. And so you want like have as high of a ceiling as possible. Ideally something that, doesn't have a ceiling or has like a very high theoretical ceiling. And also we talked about grounding these scores. We really care about being able to know what a score of like 100% means on this bench. And you can't really know that unless you have some comparison point to humans, and ideally expert humans, people that are extremely talented at the thing that they're trying to do, because that's the threshold at which we care about like AI R&D automation. And so like these are some like wish lists that we care about from our evals. Also, we'd like to have smooth scaling. This is somewhat harder than we initially thought. So we ideally want performance to be predictable with elicitation effort. So to be able to characterize that, like, hey, if I put in like, X amount of elicitation effort, I'd expect like some smooth scaling of performance on my evals. In practice, this has been observed to be somewhat difficult for most types of elicitation, except some elicitation things that we will get to, like best of K. The idea is then that we can, calculate a buffer from this and be like, look, if somebody spends an obscene amount of time or money into elicitation, even then they can only get this much of a jump. And so that's like where we should set our buffer of like where we should raise the alarm for like AR&D automation. Also, we'd want a wide range of tasks, not bottlenecked on single failure modes. These are things that like, you want your benchmark to be, if there are certain types of tasks that are like models are failing at because of like specific failure modes, and then labs improve them over like the course of a few months, you will suddenly have a very big jump in performance on your benchmark. So you don't really want to do that, and like one way to avoid that is try to get like very diverse tasks. So you're not really having like a single failure mode. Yeah, and so we created 7 tasks. We can talk about them in more detail after as well. Some examples are like, for example, optimizing a kernel. So the task is you have a prefix sum function that you have to try to make as fast as possible while still incorrect on some really large input, and like that's effectively your score. And the best human solutions tend to use Triton, and they're just like really optimized kernels. Models also do that, surprisingly. Teaser. Other environments include something like a restricted architecture, like language model. So we've removed certain primitives, like no division, no exponentiation, and so you kind of have to come up with like creative things to do in order to like actually implement the language model. And then like we score them by just like how good is your loss on open web text. Yeah, these are the kinds of tasks. There's like a couple of others that are like also, experimentation based. So there's something that's like scaling law experiment, where we effectively restrict how many flops that you can use in training, and you're supposed to predict loss and think like the optimal hyperparameters for like a much larger training run. The idea is that you kind of like try to derive a scaling law. Various other environments like that. The other thing that's really important that we talked about is human baselines. So we have a bunch of really talented baseliners. They came from three main sources. We reached out to like PhD students at like top grad schools. We reached out to people that were professional networks, people that had like 5+ years of relevant experience or like worked at like top organizations like labs and other like research places that were like, we knew that we were like, they were really talented. Also, we used this as a as the final stage in our hiring pipeline. So people had to pass a pretty high bar before we used them for baselines. We have about 10 runs per environment on average. Some environments have some more runs, but like, I think at least 8 for all of them. So we think that this is like at least somewhat representative of like how good really good humans do on these tasks. It is important to note that this was somewhat unexpected. I mean, maybe not unexpected, but we didn't. We saw this and we were like, huh, is that like the distribution of scores is from like different sources is quite strange or like quite different. Like our hiring pipeline, I think, has a much lower average score. Our professional networks have like really good scores, right? Because presumably there's like not that many of them, but they're all really, really talented. And our hiring network has just a much wider pool. And so like some people can do really well in the early stages and then not really quite perform as well as these other really talented people. And then PhD students are somewhere in the middle. Yeah, I think I'll talk about results soon, but this was just somewhat set up about the basic thing. I expect most people to sort of have a rough sense of the lay of the land. But take questions here for anything about this so far. Questions in Zoom? Cool. Awesome. So we can talk about results, which is, I think, the more interesting part for today anyway. So yeah, how hard are the actual tasks? So pretty hard. Even like, really, really good humans don't really make that much performance, that much of a increase in score in 2 hours. So like even like the 90th percentile is like somewhat sitting at like 0.2 like normalized score. And for reference, these scores are normalized to what we call a reference solution. So people who made the task, like people who work at Meter, they tried really hard with like, specific knowledge of the task and the domain area to come up with a solution that they think is really good and like representative of like an expert solution. And that gets normalized to 1. Sometimes our baseliners beat that. So you can have scores above 1. And sometimes they can really beat that. So you can have scores like substantially above 1. But that's like basically and 0 is the starting solution. So we provide like a very basic solution for them. But yeah, like, so you can see like on the median like expert human gets to like 0.6 something, close to 0.7. So these tasks are pretty hard. There's like still a decent amount of range amongst the performance of humans. But then how do the models do? So yeah, the models they make a lot of progress in 2 hours relative to humans. That makes some sense. There's a lot of advantages to being a model. You can spit out code really fast. You can maybe read things really quickly. But then as humans continue to work on the problem, humans also spend a bunch of time understanding what to do. Whereas models kind of just immediately start going at like a first pass of the problem. But yeah, as you get past like 4 hours, humans start catching up and start doing eventually much, much better. But yeah, so one thing that we noticed is that scaffolding really, really matters when it comes to model performance. For example, like the way that you choose to spend your time, so we give everyone 8 hours, models and humans. You could do one big 8-hour run with a single model, right? But we've noticed that that's actually not very good. And it's much better to give models like multiple tries with like smaller time chunks. So it's like some sense you like do 30 minutes, you like wipe your context, you do 30 minutes again, wipe your context, and you keep doing that, and you like just take the best one that you did. They're given access to the score while they do the task. So you can do this. This is like a reasonable strategy. And yeah, models like differentially perform better in these cases. Like some like O1 preview performs better with like slightly longer allocations. Claude is much better with like shorter allocations. So it's kind of interesting to see that like these are, and these like correlate with like different like strategies almost, or like how models work. Also on our like other task suite, this is not REbench, but this is like general autonomy. We see an even bigger jump in like very short amounts of elicitation. So just like 2 engineering days, we got a huge improvement on like our autonomy test suite for O1 preview when we were trying this. The other thing that we did in this set of in the REbench paper is what we call best of K. Now, extending the idea of this like different time allocation, like one thing you could think of doing is like, okay, what if I like keep doing this, right? Like I can just keep taking more samples, assuming that I've got more budget. This is like one way to spend all my time, or like one way to like basically be like, okay, I've got some amount of dollars, how many, or like time budget, what kind of performance can I get if I'm willing to spend more? And we see like it scales pretty smoothly. It's like, so the way we did this graph is like we just ran a bunch of runs and then started sampling, and we bootstrapped to get like these confidence intervals. And so this was like, so 64 runs of 30 minutes is like much more than 8 hours. Like it's so like 32 hours of runs. So that's like a much bigger like run set, but like models can get quite good performance if you like give them that kind of budget to work with. And some of the things that we thought about after doing this work were like, hey, okay, so can we elicit this? Like this was done post running, right? Like this is analysis of results after running a bunch of runs. Could you do this ahead of time? Could you like build in like this like best of K-ness into an agent and like elicit this performance like ahead of time on like longer tasks? Yeah, so this is stuff that we thought were like interesting. Also true with 2 hours, like you just see pretty smooth scaling going up. And then so we're like, okay, let's make the number go up, like push this out as far as we can. These are like somewhat unofficial results. This was just like an experiment I ran like after the paper was out. It was not very carefully. We didn't examine all the runs in the same way that we did for the official stuff. So take this with a grain of salt. But yeah, we do start seeing like, model performance plateau after like a bunch of samples. For like, we did this only for 2 tasks. So there's like a scaffolding task and the kernel task that we talked about. And it's interesting because I think what some analysis of these runs, I think points to just like not enough diversity in like it starts getting kind of the same set of solutions. There's not enough diversity to like continue to like select on the score. And this works better in tasks, or like this is more like salient in tasks that don't have quite so much noise in their scoring function, because otherwise we'd just be selecting for noise. So like that's why we pick these tasks. These tasks don't really have any noise. Yeah. Pause here for questions. Anyone? Yeah.
Yeah, my question is how you get the like scores over time. Like what does it mean for a model like Sonnet to work on it for 2 hours versus 30 minutes? Like is it a human interaction or yeah, how does that work?
Yeah, so we have effectively like an agent loop. You can think of it. There's an environment. The model is given the task prompt and it's like messages. Well, like, okay, what do you like? What's the next completion? It can use tools. So if it uses tools to interact with the environment, we'll get like results from those tools, append that to the context, and then that's like the loop that works. And we set the token limit, like there's like effectively unbounded tokens. And so the only thing that matters is how much time it's been spending. And that's how like we get scores over time. So like one of the tools that has access to is score, in addition to Bash tools, Python tools, various other tools like that. And that's what it means. So like a 30-minute run would be like, it tries for 30 minutes with like a REPL loop with some summarization of files and all that kind of stuff. And 2 hours would be the same thing, just over like a longer time period.
And so each time it like maybe stops, you kind of reinitialize it with a new window with the score and all the outputs of the previous attempt.
Yeah, it wouldn't be reinitializing, but it'd just be like appending the results to the previous results, and then you just feed that back in. It depends on the scaffold though. So certain scaffolds don't work like this. So for like O1 preview, we used the AID scaffold, which is like an open source agent framework. And it's the same one that like OpenAI used in MLEbench, just fair enough. And what we did there, so the way that one works is it's somewhat different, where like that one will try, I'm going to make one Python file that is my solution, and I'm going to try running that, and like, then like that like automatically runs for, sorry. And then the way that works for 2 hours, it just keeps trying to optimize that one Python file. It doesn't have the same like look at the previous context, try again. It works differently, but yeah, you could choose to spend your 2 hours in all of these ways.
Have any sense of rough numbers of how many turns are done during these?
Rough numbers. Okay. I don't have precise numbers. I think like for 30-minute runs, I want to say like 50 turns.
Okay, I mean, I guess my bigger question is around like the 8 hours at one that
Yep.
you showed for O1.
Yep.
I'm a little confused. Like, yeah, how did you get that within like limits of turns and tokens?
Yep.
How did that go on for 8 hours? Was it mostly like almost all execution time, or what was going on there?
Right. So it depends on the task. So a couple of things. The 8-hour one for O1 preview uses the aid scaffold that I just talked about, where it's like trying to optimize this one Python file. And so you could imagine that there isn't like a big buildup of context, right? So in some sense, the turns are not really quite relevant here. It's just trying a bunch of times to like optimize this. Like it'll generate like 5 solutions and like do like a one-step tree search effectively. Other models, like if we ran like when we ran Claude on like the modular framework, that one will have a bunch of turns. I don't quite know how many turns that would be for 8 hours, but older conversations get summarized. So the full output is saved in a file and it's told that, hey, like this is a summary or like a truncation. The full output is here. You can run this bash command to get the full output if you want.
Okay.
For like older conversations. So like that's how you'd handle the context and stuff like that. Yes.
Hey, this is really very interesting. I guess I've got two questions. So one is like I've heard people be a bit skeptical about AI R&D because they say, well, it's mostly limited by like the amount of compute that you have to actually run experiments.
Yep.
So I guess have you noticed that like the models do better if you just give them like, 2 GPUs or instead of 1 GPU?
It's interesting. So we get most of our tasks, they have somewhere between like one has no GPUs, which is like a scaffolding task. You interact with an API. And then scaling law task has 6 H100s. So we have anywhere between like 0 to 1 to like 6 H100s for at any point. We actually see that models don't use their compute very effectively. That like GPU utilization is really bad for a bunch of reasons. Like they're not able to, handle things like VRAM issues. They're not able to handle like they're just not able to really manage their experiments well. So we kind of see that in a lot of cases. So I'd expect no real performance gain by like increasing access to compute. I think as models get better, this will become much more resilient. You had another question?
Yeah, tiny second question.
Mhm.
I guess it could be interesting to plot the like human best of n on the plot you have with best of n. I guess you could kind of read it off from like the percentiles, but it would
Yeah.
also be, I think, be better than O1.
Yep,
at least
yep.
the
I have a plot that I should have included, but I forgot to include it. I will show that to you in like towards the end.
Sure.
It has like the answer that you're looking for. Other question? Yeah.
Do you think that in like the next generation of reasoning models, we'll see labs using best of n kind of style to make their completions better?
I mean, I would imagine they already do some of this, I feel like, because I think majority voting was like used when the O3 thing was announced for a lot of benchmarks. They had like majority voting and then not majority voting. It's not quite the same as best of n because like, you don't like we're using ground truth score, whereas like a majority vote is like, okay, I don't have the actual verifier. Like, what would I do? Just take the majority. Yeah, with like if you have like an ORM or like a process like a reward model or like an outcome reward model, you might be able to use that to like estimate best event. I'd expect some of that. Also, I think O1 Pro, I don't know how exactly it works, but my understanding is that some amount of like search over solutions in some sense. So that's kind of similar to this. Yeah, I'd expect more of that in the future. Or like something that's like this or better, maybe. Yes.
Relatedly, I'm not totally sure how you would set this up. Like
Yep.
maybe it'd be like looking at the number of reasoning tokens used or something, but I'm curious about the extent to which it looks like O1 preview is just internally literally using, or like how is like O1's token use scaling comparing to if you were just doing best event or something? Like is it sort of just trained to do this sort of like restarting and evaluation internally, or is it doing something fancier?
I see what you're saying. It's maybe we don't have access to the chain of thought, so it's that would be the way you would actually do it. And so maybe with like R1 or something, we could do something like this. But I think some amount of like the differences here is that like the solution, you don't actually have the verifier for your like intermediate chain of thought steps, right? So like it's in some sense a different hierarchy of like best of ending. Your best of ending over like intermediate steps, and then your best of ending over like your solution, attempt. And so like I think there's a difference there. But yeah, one way to do this is like if you get access to the reasoning effort thing, you could try doing it that way, like low, high, medium, see how that scales. One way of thinking about this. I had yes.
How much more of an AI researcher's job is there this doesn't cover? Like, what are some other like important things they do that aren't covered by this? And sort of like similar question is just like, how much does this tell me about whether AI research is about to be automated?
Yeah, so we have a section about caveats. I'll get to that in shortly. So just talk about that. Anyone else?
We have one question from the chat. This one's from Adria. He asks, how difficult is it to specify score for a task? Would this work without a hard specification of the score, just, for example, a command to run and a model to judge? I've been trying to use AIDE within the editor to get machine learning engineering work done, and lack of verification of task has been a problem.
Yeah, so it's somewhat non-trivial to set up a score function for some tasks. It's really easy. Like imagine if you're just trying to train a model in a specific setting, you just have loss. Like your validation loss is a score that you care about. It's like very natural, easy access. If you're trying to optimize runtime, you've got easy access to like how long it takes on a given input. So certain types of tasks are like I think amenable to like easy scoring, and many types of tasks are not. Like imagine if one of the ML engineering tasks you care about is like building a new tokenizer library. What's the score? Like it's kind of hard. You have to set up tests and like hope that those tests are enough. Other things that you might care about are like, yeah, if you have like an LM as a judge type of thing, then like that is somewhat noisy, but maybe like somewhat reasonable. Yeah, and this is sort of related to the limitations about like what kind of ML engineering work is not covered by this, like yeah, automation stuff. The types of all of our tasks are like in some sense very easily verifiable. Like we have a true answer, we have a score function. These are like easy to specify. So I would imagine that like a good chunk of tasks where like this isn't the case means that you run into difficulty applying these kinds of methods. Good.
Have you run this with O1 or R1?
I think I'm not sure about this. Other people know this more than I do. So maybe just stay tuned and we'll have reports if we have. So cool. I guess I'll jump to the next little bits. Yeah. So yeah, I think some of the cool things that I thought would be interesting to go over are like some interesting like transcripts that we saw of like analysis of runs. So one of the runs is you have a like LLM Foundry like from like Mosaic. We're using their library, and your job is to improve the performance of a fine-tuning script, like make it run faster while keeping the same like close to the same loss. And so one of the things that O1 Preview decided to do is just copy the reference model as the trained model, modify the weights slightly so that it looks like we trained things, output log training like actually just made up log training loss stuff in the terminal. So it looks like we trained things. And then look, I eliminated all of the unnecessary steps by bypassing data preparation, training, model conversion. We've reduced the runtime so much. So it was kind of interesting to see that like O1 Preview found this like somewhat exploitative cheating solution. Like the instructions explicitly said that you must actually fine tune from the base model. So like it is very clearly like it's not like a allowed, but oh, you missed the spirit of the task. It's just actually a cheating task. Our scripts just didn't catch it. But it was somewhat interesting to see like this in some sense is like kind of like reward hacking of the environment. So it was kind of interesting to see that like yeah we got these kinds of results from this. Other stuff that we saw, yeah, agents often really are not able to understand, like are not great at problem solving in this like long horizon-y way. You often see tasks where like they'll do something, make a worse solution, like make something that's like slightly better than the starting solution, and then make something that's much worse, not realize that they probably should go back to the much better solution and retry from there. Yeah, they just don't have this inherent like backtracking capability yet. So that's one thing. We also saw some environments have lucky guessing. This is the small scaling law experiment that I talked about. It just starts adding fudge factors. So 1/9, negative 0.045, all of this is just fudge factors that adds until the score goes up. And it gets to like almost a reference score. Like the small scaling law is one where like there's only like 1 is the ceiling. You can't do better than 1 because there's just like a true score. It gets to 0.99, which is like pretty close. And it's somewhat interesting to also see that like this is exploiting the fact that we're providing it with ground truth score, so it's just like trying to hill climb effectively without actually doing any experimentations. So this is some sense like a flaw of our task that we didn't foresee that like models would try and exploit, and like kind of only highlights like how hard it is to really make good solid tasks that don't have this kind of behavior. But other interesting good solutions, there are like also some really good solutions. So the best kernel solution was better than that O1 preview found, was faster than any of our baseline solutions. So all the expert humans that tried it, they were like not as good as O1 preview. And like actually works. Like this is not cheesing it. This is like a good solution. Tries different block sizes, actually does like custom kernel stuff. I haven't copied this kernel out, but it actually does sensible things, which was really impressive. This was like one of the highlight results from like our like good solutions bucket. And yeah, and then it just does things. And yeah, I guess we can go to limitations. So biggest limitation by far, we only have 7 tasks. That's not very many tasks. It falls far short of other benchmarks that have like 30 to 100 tasks. And it's a very, very small sample size. So some amount of like, I think you'd asked the question about like how representative is this? So we really don't have hard sweet tasks. That is pretty much a good chunk of like frontier ML engineering work, like interacting with really large code bases. We don't have these tasks are like very like greenfield encapsulated into like small buckets. Like you start with a very clean repo. It's like a few thousand lines of code. You kind of only have to work on like 2 or 3 files. Realistic work is like you have a million lines of code, like 4 different subsystems that all interact in like non-obvious ways that are like not even explicitly laid out in code. There's like some other like, endpoints that it's hitting or something. And like that's much more challenging to deal with. And so I fully expect like models that we ran on today would not be able to transfer very effectively to those settings when these much more like messy and like non-nicely encapsulated code bases. Yeah, we still don't have a good sense on the elicitation gap. We have some sense on this best of k thing, but we don't know if that's like, how much can you just like elicit that out in like an actual agent? We don't know how much more performances are on the table. Like, can you actually like elicit some of these capabilities, especially with, the newer models that are like much more advanced in their reasoning capabilities. Yeah, and also, yeah, frontier research often takes months, and it's like on the scale of like, many weeks to many months. These are 8-hour tasks. These would fall like a very short chunk of those kinds of work. And I fully expect models to not be able to do things that are like a longer horizon than this. They already can't do very much. Like you have to do this best of k thing on like 30-minute chunks or 2-hour chunks, right? If you just did them for 8 hours, they wouldn't work so well. Also, unrealistic feedback, yes, as we talked about earlier, there isn't really like a lot of tasks don't have score functions available easily. And so we do need to like see what does that look like in these cases. If you're accepting like a PR from like a model, like there isn't a score function. You're evaluating a bunch of stuff. So like capturing this like manual review essence is really important. What we're going to try to do, maybe make more tasks. Try to get like 20 to 30. That would be cool. A wider range of key skills, interfacing with large code bases, trying to get manual review, trying to do longer baselines. We tried to do some group baselines and some longer baselines of like 24 hours, like over 3 days. But we're still like getting the results from that. Yeah, and then like future elicitation, trying to build more tools for that, more frameworks. We're actually a little bit unsure about how important this will be going forward. As models just get better and better, will elicitation matter less? It's not clear, especially with like reasoning models. It's some of this stuff might completely change once we have access to more powerful reasoning models, right? It's not clear. Yeah, learnings and takeaways. This stuff is pretty hard to do in like a sensible way. You run into things like, limitations of tasks that you didn't foresee that models start exploiting. Certain things are quite hard. Like, yeah, I don't have a slide for that, but like we use floating point checks, which is difficult to work with sometimes. If you use LLMs as a judge, often that can be a pretty big source of noise. Like, those are stochastic, and so you're just not gonna. Those scores can have pretty high variance even for like the same solution, and that's kind of annoying to deal with. It reduces the signal that you have. Elicitation is also hard to solve. We talked about that. Yeah, even when we tried really, really hard, there were like, some tasks like were saturated. Like optimized kernel got pretty close to like a theoretical runtime limit. There's only so fast you can make a kernel for that particular task. Certain tasks were also pretty close to saturation. It was pretty hard to like, some tasks have high variance. We talked about that. Some tasks had a lot of major, like, 2 out of 11, like, based on others experienced major technical issues. And these are like just show the challenge of making really realistic things that are close to the frontier. And even these things aren't like anywhere like actually that close to the frontier for like all the limitations we mentioned. I think like just that extra like last mile is going to be even more challenging than we thought. Yeah, I talked about some of this. Yeah, and then agent solutions look very different from human solutions. We talked a little bit about how agents like tend to, try a bunch of small things, and then in some sense they seem to be overfit. Like you see the, adding fudge factors until it just works. If you like tweak some of the parameters of that task, suddenly this wouldn't work. Whereas like human solutions would actually just generalize pretty well because they're somewhat trying to follow the actual task. Long horizons seem to be really, really challenging still. Qualitatively, like agents get stuck into loops, don't really stay much on track. We'd like to coordinate this kind of stuff along with the research community, get more tasks done. They'd be pretty cool. We do actually have public accessible run transcripts. So it's not coming soon, but it's out. It's like transcripts.meter.org. So if you want to look at some agent transcripts, they're all publicly accessible now. And we're trying to get more people to adopt this eval. Labs, other research organizations, people that want to see how close things are to R&D automation. Yeah. Yeah, summary, any questions? Sure, I'll stop a little bit more before I jump into other stuff. More questions?
We do have some questions from the chat that we can get to. Okay. So first question, how does the agent scaffolding handle when models give up on working on the task, and how do these model quitting outcomes show up in your experimental results?
It's not that common. I think sometimes models will decide that things are out of scope. Like one task is fixed embedding, which is like we take a language model, we like jumble up the embeddings, and we're like, hey, this is like our language model. Your task is to recover performance. The straightforward way to solve that task is to retrain the embedding layer. And sometimes like Cloud will be like, oh, that's out of scope, even though you have access to like an H100 and like 8 hours of compute. And so we see things like that, but then models just keep trying to do things in that limitation. I can't recall actually seeing that like I give up. I do recall like agents basically going like, okay, I've gotten to a good solution that's like 2% better than the starting solution. I'm just going to keep scoring that solution. And then it does that until out of time. Yeah, but like often we don't really see actual like true giving up.
Great. And we have another question that says, with 1000x the inference compute, what do you expect the highest percentile to be that any current model for any scaffolding could reach?
I think, so yeah, what's the current one that Owen Preview did? I forgot. Yeah, I think O1 Preview gets like something like 0.38 or something. I think with the 100x, 1000x inference compute, maybe like O1 could get, 0.8, 0.9, close to 1 maybe. Yeah, but it's unclear. I have like high error bars on that. And I'm somewhat indexing this on like the performance on benchmarks that O3 was announced with. I expect O3 with like a really high inference compute would probably be able to get like close to 1, like saturate this benchmark. In at least some tasks. I don't think in all tasks, but like maybe like half the tasks or something. But again, high error bars.
And one more from the chat. Can you chat about tasks that you made but didn't end up in the final benchmark? Were there any, and if so, what were their issues?
Yeah, there were quite a few. The issues that we mostly found were like some tasks would have like choosable solutions that were like in training sets or like tutorials like online and like are actually very easy to just one shot. Some tasks just didn't have like a high enough ceiling. Like it would be pretty easy for like an expert human to saturate them in like a couple of hours and like not really make sense to have them spend 8 hours on it. Yeah, we had a bunch of tasks like that. Like there was a lot that we like left on the cutting floor. Some of this was like a while ago, so I wasn't that familiar with them. But I could, you could email me and I could chat some more if that's interesting. Yeah. Other questions?
Is there a way for me to kind of start using an agent loop like this? Like, is there an API where I can put in my own scoring function to actually help me in my day-to-day?
Right. I would say that a few things. I think models today, you can try this. I mean, you can just set up like a REPL loop. The modular agent is public. 8 is also public. Like you can access them. There isn't, Meter doesn't have an API, but you could set it up so that like, people have done that like pretty easily. Like 8 will just work for something like this. But my like a recommendation, like we tried some like running agents on our tasks. They don't do that well. Like for like open-ended things, like making PRs for like changes or something. We found much better success using something like Cursor, where like the model suggestion or like the actions are like much more like fine-grained and like more for human uplift than autonomy. Yeah, I would expect to be much more successful to use something like Cursor than like just have this thing run in the background. But you could totally do it. Like all the code is open source. But yeah, that's it. Us happy to take questions about the overtime stuff or about anything else. Also feel free to email me. Yeah. Questions?
Do you think you're going to need to go to tasks that take humans longer than 8 hours soon, based on the saturation?
Like for RE bench, like you said, or like for
Yeah.
this. Yeah, I think so. I think we're gonna start having to, and it's a little bit unclear about how best to measure that because like beyond so certain tasks, right? Like we're getting close to like humans can do pretty well on this. 90th percentile is getting really close to the reference solution. We're gonna need harder tasks. We think that the real avenue to explore here is like this messiness concept of like, okay, why would it take someone several days to work on like a really big PR for like a really complicated code base because of this context issue, right? So we're gonna try to like see if we can grab some of that and then start measuring humans on those longer time horizons and then models on those longer time horizons. That's one avenue that we're interested in exploring. Yeah, that's sort of the shape of direction that we'd care about.
Makes sense.
Two, yeah.
So I guess I missed your intro, so feel free to cut off this question, and we can chat later. But I was wondering if you could speak a little bit about where does this fit into the safety landscape, and I guess like the argument for why a kind of safety focus org should be working on this versus leaving it to others, I guess.
Yeah. So a couple things. So when we first started making this out, we were pretty convinced that the like R&D threat model is one of the most salient ones out there because if models can start automating R&D, it is like a very rapid increase in other capabilities because like the self-improvement loop thing. So it was very important, and we didn't see good benchmarks out there on like knowing when this will happen or like having a measurable prediction or forecast of like, hey, this is like how fast models are getting better at like R&D, frontier R&D. So that's like some of the thought process. The earlier, in some sense, we were going to be making a safety case on this. Is like, look, if models can't do things that like human experts can do, and they're not capable of these skills, then like they should not be capable of like frontier automation yet, and therefore they're safe. And like they're safe for quite a while because there's like a bit of a buffer. I think that safety case is going to be harder to make in 2025 because we expect models will get more capable, especially like O3 and things like that. But we still think that it's really important to have a measure of like R&D automation, and like that's how it relates to safety. Because in some sense, like this is the thing that you would care about if you cared about other capabilities. This is one of the key things that you'd want to track. Because this is like one of the most salient ways that models can get to those other capabilities of like extreme cyber uplift or CBR and stuff or something.
Maybe I have more comments, but after
Sure.
we'll chat about
I think both of you.
Do you ever explore like human plus model?
Right. I think think humans were allowed to use models
Yeah,
in this
pretty
field.
hard to like prevent them.
Yeah, it's pretty hard to prevent that. I think we just like let them. So this in some sense is that we're thinking about maybe more like explicit uplift things in like other kinds of tasks, especially in the messiness type of tasks. I think it's kind of interesting. So yeah, maybe future work. But
I'm curious if you could comment on sort of how you think about measuring sort of messiness or
yeah.
that like amount of context needed.
Yeah, that's a very open area of like discussion and research right now at Meter. So some things are like you could imagine that like messiness is in some sense about like the thing that you're working on, how many irrelevant factors there are that you have to like sift through before you like if you have like say 10 subsystems in this like big code base of yours, and the change that you care about, you're making a change in one, it's going to impact like two others, right? The thing that you care about is 3 out of 10 subsystems, right? So in some sense, capturing this is a measure of messiness. Like one like test that we're trying to do is like, hey, if you're trying to like do something and we have a bunch of irrelevant files, right? That are like very obviously irrelevant. Humans will very quickly be able to understand that these are like useless, just not care about them. So we don't expect a big jump in or like dip in human performance, but maybe models aren't quite capable of that yet. Maybe they get distracted by these files. Maybe they're not able to understand which file to use if it's like sufficiently complicated. And then maybe we can see like some smooth model degradation in performance as we like increase the number of like irrelevant files or something. So like that's one way to measure this. There are a couple other ways that people are trying to think about, which is like yeah, other people are working on this. So if you are more interested, I think like shoot me an email. I'll connect you with the right people. Yeah. I'm just is blanking. That's one of the things. There are like a couple of other like factors that we care about.
Cool. Thanks.
Hi. So looking into the future, are you still going to be focused on research engineering tasks primarily, or perhaps have you thought about creating an agentic benchmark for, more daily tasks like booking flights and so on to kind of target the societal disruption threat model?
I think our like general autonomy suite was designed to do this. When I think it came out like last year or something. I think we're probably gonna be still focused on research engineering for instead of societal, sort of like agentic benchmarks for the moment. Just because like societal disruption is indeed like a problem and people should be focusing on it and tracking it. But we believe that like the greatest risk is coming still from like R&D automation. It is like unclear to what degree we think capabilities evals will be useful in say like the order of years. So maybe like the end of 2025, models are capable enough that it's like very hard to make capability evals where they suck at. So then maybe we might pivot to control or something. It's not clear.